The universe holds its breath in an endless, silent dark. Then, a whisper cracks the stillness. These are not stars speaking, but mysterious travelers from beyond our sun, icy wanderers called interstellar comets. And sometimes, as they streak through our cosmic neighborhood, they seem to emit bizarre and unexplained signals that science cannot fully explain. By the end of this journey, you will have explored 25 of the most perplexing cosmic enigmas ever detected, each a piece of a puzzle that challenges everything we think we know about space. We will investigate a tumbling object that accelerated without a visible engine, and a comet that flashed in perfect sync for observers across the globe. What does it truly mean to receive a message from the void? In October 2017, a telescope in Hawaii spotted a faint dot moving against the backdrop of stars. It was not following the gentle curve of an orbit within our solar system. This visitor, named Oumuamua, meaning scout in Hawaiian, was racing on a trajectory that could only have begun around another star. Its very arrival was historic, the first confirmed interstellar object ever seen passing through our cosmic backyard. But its true strangeness was only just beginning to reveal itself. As astronomers trained their instruments on it, they found a shape unlike any typical comet or asteroid. The way its brightness flickered suggested it was tumbling end over end, elongated like a cosmic cigar or perhaps a flattened pancake. More puzzling was what was missing. When a comet approaches the sun, its ice heats up and erupts, forming a glowing cloud of gas and dust called a coma, and often a beautiful tail. Oumuamua had none. It showed no visible coma, no tail, just a dark, rocky-looking object. Yet as it sped away from the sun, something impossible happened. Its path could not be explained by gravity alone. It was accelerating as if pushed by some unseen force. For a comet, this push comes from the jetting of gases, but without a visible coma, where was the gas coming from? This non-gravitational acceleration sparked intense debate. Some proposed exotic natural explanations, like it being a chunk of solid hydrogen ice evaporating invisibly, or a dusty fractal aggregate falling apart. Others, including a prominent astronomer, raised a more provocative possibility. Could this acceleration be from light pressure on a giant, thin sail? The idea of an artificial object, a derelict probe or a piece of alien technology, entered the scientific conversation not as a claim but as a hypothesis to be tested. The SETI Institute listened intently, scanning Oumuamua for any hint of artificial radio signals. They heard only the deep silence of space. The debate raged in journals and conferences, a testament to how a single, silent traveler could expose the limits of our understanding. Was it a weirdly shaped comet venting gas in a way we could not see, or something entirely stranger? Oumuamua left our neighborhood as swiftly as it arrived, a fading dot carrying its secrets back into the interstellar dark. But it left behind a profound question. If the first visitor we ever met defied all our expectations, what else is out there, tumbling silently toward us? The silence from Oumuamua did not stop the scientists. Faced with an object that accelerated without a visible engine, they began to propose radical but natural solutions. One leading idea suggested it was not a rock at all, but a cosmic iceberg made of frozen hydrogen. Picture the coldest object you can imagine, then make it far colder. A hydrogen iceberg formed in the dense core of a giant molecular cloud would be nearly invisible. As it neared our sun, the heat would cause the solid hydrogen to turn directly into a gas, a process called sublimation. This venting gas could provide the gentle push that altered its trajectory, all while leaving no dusty coma for our telescopes to see. It was an elegant answer, but it came with a cosmic catch. Such an object would be incredibly fragile, evaporating rapidly in interstellar space. Could it have survived a journey that might have lasted millions of years? Another theory proposed a different kind of ice, frozen nitrogen, similar to what we find on the surface of Pluto. A chunk breaking off from a distant, Pluto-like world could also explain the acceleration and the strange shape. Yet each natural explanation stretched the limits of known physics, requiring just the right conditions in just the right way. Then there was the more speculative idea, the one that captured the public imagination. What if the acceleration was not from gas but from light? Sunlight itself exerts a tiny pressure. For a spacecraft, a large, ultra-thin reflective sail could catch this photon breeze and accelerate across the stars. Some scientists noted that Oumuamua's estimated shape and motion were consistent with a lightweight object being pushed by light. This was not a declaration of discovery, but a call to keep an open mind. The true legacy of Oumuamua is not a single answer, but a fundamental shift in perspective. It taught us that the catalogue of cosmic objects is far stranger than our textbooks described. It forced astronomers to look harder and think more creatively. Most importantly, it proved we were not looking at an empty ocean. The first fish we pulled from the interstellar deep was utterly bizarre, which meant there was certainly more to find. The hunt was now officially on, and the next visitor would arrive sooner than anyone expected. Just 2 years after Oumuamua's enigmatic departure, the cosmos sent us another calling card. In August 2019, an amateur astronomer in Crimea named Gennady Borisov spotted a fuzzy new visitor. This object, soon named 2I/Borisov in his honor, was unmistakably interstellar. But unlike its tumbling, tailless predecessor, Borisov looked comfortingly familiar. As it approached the Sun, it developed a brilliant classic coma and a stunning long tail of dust and gas. It was a textbook interstellar comet, a frozen traveler from another star system behaving exactly as our models predicted. For scientists, it was a welcome chance to study a more typical specimen, to compare its chemistry to our own solar system's comets. The mystery seemed to be over before it began. Then, the Allen Telescope Array in California turned its dishes toward the comet. This network of radio telescopes, designed to search for technosignatures from distant civilizations, was listening for any unusual radio emissions. In the quiet background hum of space, analysts noticed a brief, sharp spike in the data, a radio burst that appeared to originate from the direction of Comet Borisov. It was not a repeating pattern or a structured message. It was a single, unexplained blip. The immediate question was not about aliens, but about error. Could this signal be a simple glitch? Radio astronomy is a field perpetually under siege by human-made noise. A passing satellite, a stray cell phone tower, even a microwave oven in the observatory kitchen can inject false signals into the delicate data. The team began the meticulous process of elimination, checking satellite trajectories, local interference logs, and the health of their own equipment. The burst did not match any known satellite signature, and it seemed to track with the comet's position in the sky. Yet, the association was maddeningly difficult to prove. Comets themselves are not expected to be strong sources of such radio bursts. While they can interact with the solar wind to produce complex plasma effects, a singular, powerful spike was unusual. The signal was also incredibly faint and fleeting, a whisper lost in the cosmic static. Without a repeat performance, confirmation was nearly impossible. Was it a rare natural outburst from the comet's nucleus, a crackle of energy from a collapsing pocket of gas? Or was it more mundanely a piece of space junk we had not yet catalogued, reflecting a signal from Earth in just the right way to fool the telescopes? The investigation ultimately leaned toward a terrestrial or instrumental origin, a phantom in the machine, but the case was never fully closed. Borisov's radio burst serves as a critical lesson in cosmic detective work. It highlights the immense challenge of interpreting a single, unverified signal from a fast-moving point of light millions of miles away. it reminds us that every potential discovery must first run a gauntlet of doubt, where the most exciting answer is often the least likely. The true signal from Borisov was not in that brief radio blip, but in the silence that followed, a silence that deepened the mystery of what exactly we should be listening for. The quiet departure of Comet Borisov left astronomers listening harder than ever, straining to hear meaning in the cosmic noise. Then, in 2021, a scientific paper ignited a firestorm of debate by pointing a finger at one of the most famous mysteries in the history of SETI, the WOW signal. For 72 seconds in August 1977, a radio telescope in Ohio recorded a signal so powerful and so unusual that the astronomer who found it scribbled "WOW" in the margin of the data printout. It came from the direction of the constellation Sagittarius, was never heard again, and for decades its origin remained utterly unknown. The new study proposed a radical and controversial source. What if the WOW signal was not from a distant star, but from something much closer, something passing through our own solar system? The researchers suggested it could have been emitted by the hydrogen cloud surrounding an interstellar comet, one that was completely invisible to optical telescopes at the time. Their methodology was a fascinating exercise in cosmic backtracking. They calculated that if a comet were venting hydrogen gas, that cloud could amplify and reflect the constant radio whispers of our own Milky Way galaxy, creating a brief, intense burst detectable from Earth. By scanning along the hypothetical trajectories such a comet might have taken, they claimed to find a potential match, a path that would align the comet's position with the exact patch of sky and the exact moment the WOW signal was heard. It was a compelling, elegant idea, a way to solve a 44-year-old puzzle with a natural, if exotic, explanation. The scientific community, however, met the claim with intense skepticism. The core challenge is one of overwhelming noise. Our planet is drowning in a sea of human-made radio signals, from television broadcasts and radar pulses to satellite transmissions, and even faint leakage from everyday electronics. Distinguishing a true cosmic signal from this cacophony is like trying to hear a single whispered word in the middle of a roaring stadium. Furthermore, the original WOW signal had characteristics that made a simple cometary reflection seem unlikely. It was observed on only one of the telescope's two receivers, which were tuned to slightly different frequencies, a pattern not easily explained by a broad, natural emission. Critics argued the study's proposed comet trajectory was just one of many possible paths, and that finding a match after the fact could be a statistical coincidence, not a discovery. The controversy highlights the immense difficulty of the search itself. Every potential technosignature must pass through a ruthless filter of doubt. Is it repeatable? Is it consistent across multiple instruments? Can every possible source of human error or interference be ruled out? The 2021 paper did not close the case on the WOW signal. Instead, it reopened it in a new and provocative way, reminding us that our first contact with something beyond our world might not be a clear message from a distant star. It might be a fleeting, ambiguous echo from a silent, icy wanderer that passed through our backyard, unaware it had even spoken. While the radio whispers from Borisov proved elusive, the comet carried a different kind of message written in pure light. As it blazed across the sky, astronomers performed a fundamental act of cosmic chemistry. They broke its light apart into a spectrum, a rainbow barcode that reveals the specific fingerprints of every molecule boiling off its surface. In the familiar comets of our own solar system, this barcode has a predictable pattern. We see the signatures of water vapor, carbon dioxide, and certain simple compounds like cyanogen, a gas composed of carbon and nitrogen. When scientists pointed their spectrographs at Interstellar Comet C 2019 Q4 Borisov, they expected a similar, if slightly varied, readout. What they got was a profound surprise. The spectral lines were there, but their intensities were all wrong. the signal for cyanogen gas in particular was astonishingly strong. It shone far brighter in the spectrum than it does for any local comet, suggesting the comet's nucleus was releasing this volatile compound in massive, unexpected quantities. This was more than a minor difference. It was a chemical shout from an alien system. A comet's composition is a frozen record of the conditions in its birth cloud, the swirling disk of gas and dust that surrounded its infant star. The strength of certain lines tells a story about temperature, pressure, and chemistry from billions of years ago and light years away. The anomalous lines from Borisov painted a picture of a formation environment radically different from our own. Perhaps its home system had a much richer reservoir of nitrogen, or its particular region of the protoplanetary disk was far colder, allowing different kinds of ice to condense onto its nucleus. The puzzle was not just the presence of these molecules, but their staggering abundance. It forced a humbling realization. Our solar system, with its specific blend of ingredients and its particular recipe for making comets, might be just one flavor in a cosmic ice cream shop of infinite variety. Borisov was not a slightly odd cousin from across town. It was a complete stranger from a country with different natural laws of chemistry. Its very substance whispered of alien temperatures, alien pressures, and an alien history written in atomic bonds we are only beginning to decode. This silent chemical message, far clearer than any radio burst, told us that the building blocks of other worlds can be assembled in ways we never dreamed, carrying within their frozen hearts the unique signature of a sun we will never see. The chemical signature of Borisov was a quiet revelation, but the cosmos was not done with its tricks. In the late 1990s, a different kind of signal emerged, one that seemed to beat with the mechanical precision of a cosmic clock. As the giant comet Hale-Bopp swept through our inner solar system, radio telescopes detected something extraordinary. Amid the chaotic noise of its gaseous envelope, a pattern emerged, a series of sharp, powerful radio bursts that repeated with a steady, rhythmic pulse. To the astronomers listening, it was an uncanny echo, a perfect mimic of one of the universe's most famous natural lighthouses, a pulsar. These are the rapidly spinning corpses of massive stars, beaming radiation like a lighthouse with such regularity you could set your watch by it. Yet here was a simple ball of ice and dust, apparently broadcasting its own artificial-sounding heartbeat. The explanation lies in the violent frontier where a comet meets the sun's fury. The sun does not just shine light, it blows a ceaseless hurricane of charged particles called the solar wind. When this supersonic stream slams into the gas cloud surrounding a comet, it creates a turbulent shock wave, a bow shock, like the wave before a speeding boat. In this chaotic region, complex plasma physics takes over. The interaction can generate intense bursts of radio waves through a process akin to natural amplification. Electrons get caught in magnetic fields, whipping around and releasing energy as radio noise. Normally, this produces a hiss of static, a broad-spectrum roar. But under very specific conditions, with the right density of gas, the right strength of solar wind, and the right geometry, the system can fall into a feedback loop. Think of it like a microphone too close to a speaker, a screech of pure tone emerging from the noise. In Comet Hale-Bopp's case, the entire comet solar wind system briefly became a natural radio oscillator. The repeating pulses were not a message, but a resonance, the entire interaction region ringing like a bell struck by the solar wind. It was a stunning demonstration of how nature can produce signals of breathtaking regularity from utter chaos, a reminder that the universe often wears the mask of the artificial to hide its deepest, most complex natural processes. Even the most familiar cosmic processes can hide shocking secrets in plain sight. While Comet Hale-Bopp's radio pulses were a natural resonance, another type of signal from a different visitor defied every expectation about what a cold, dark object should be capable of doing. This is the story of the dark comet's X-ray flare. In our solar system, when a typical comet like Hale-Bopp nears the Sun, it often produces a soft glow of X-rays. This isn't from the nucleus itself heating up, but from a fascinating dance at the atomic level called charge exchange. The Sun's hurricane of charged particles, the solar wind, smashes into the comet's vast cloud of neutral gas. During this violent collision, electrons can be stripped from the comet's gas atoms and captured by the solar wind ions. When those captured electrons settle into a lower energy state, they release the excess energy as an X-ray photon. It's a beautiful, well-understood process, a luminous signature of interaction. But then astronomers pointed the Chandra X-ray Observatory at a different kind of visitor, a dark interstellar object that showed no visible signs of activity. It had no glowing coma, no sweeping tail of dust or gas. By all traditional measures, it was inert, a silent, frozen rock tumbling through the void. Yet, against all odds, Chandra detected a distinct, flaring X-ray signal coming directly from it. The discovery was immediately perplexing. How could an object with no visible gas produce the X-rays that require gas to create? The charge exchange mechanism seemed impossible without a cloud of neutral atoms for the solar wind to interact with. Scientists were forced to reconsider the object's true nature. One theory proposed that it was in fact a very faint comet after all, but one with an almost invisible coma. Instead of the bright, dusty cloud we expect, perhaps it was venting an extremely tenuous stream of gas, too faint for optical telescopes to see but just dense enough for the sensitive X-ray instruments to detect an interaction. Another, more radical idea looked at composition. What if this wasn't a comet at all, but a rocky or metallic asteroid? If its surface was rich in certain metals, the impact of high-energy solar wind particles could theoretically cause it to fluoresce, emitting X-rays in a different way, like striking a cosmic bell. A third possibility pointed to something even more energetic happening just beneath the surface. Could there be pockets of volatile ices trapped under a dark crust, erupting in tiny, localized jets when heated? These microjets would be too small to form a traditional tail, but their sudden release could create a brief, intense interaction zone with the solar wind, resulting in a flare. The dark comet's X-ray signal remains an open case, a powerful reminder that our categories are often too rigid. It challenges the very line we draw between a lively comet and a dead asteroid, suggesting that in the cold depths of space, even silent wanderers might hold hidden, energetic hearts. A promising signal can be the most maddening kind of all, deep within the data streams of a deep space network antenna. Tasked with listening to our own distant spacecraft, an analyst noticed something out of place. It was a narrowband signal, a sharp spike on a single frequency, the kind of signature often associated with artificial transmission rather than the broad, messy noise of natural cosmic events. Even more intriguing, its apparent point of origin coincided with the predicted position of a newly discovered interstellar comet, a faint speck of ice on a one-way journey through our solar system. The alignment was not perfect, but it was close enough to send a ripple of cautious excitement through a small circle of researchers. Here was a signal with the right characteristics, appearing in the right place at the right time. Procedures were initiated, follow-up observations were scheduled at other facilities to triangulate the source and listen for a repeat. This was the critical moment, the test that separates a cosmic whisper from a phantom. When the larger, more sensitive telescopes swung into position, they found only silence. The signal had vanished completely. It never returned, not in hours of dedicated listening, not in subsequent days. The promising blip was gone as if it had never been. The investigation that followed was a lesson in humility. Every link in the chain was scrutinized. Could it have been an instrumental glitch, a brief surge of power within the antenna's own electronics mimicking a cosmic event? The equipment logs showed nothing abnormal. Could it have been a reflection from a piece of human-made space debris, a defunct satellite or a discarded rocket booster tumbling in orbit, accidentally bouncing a signal from Earth back to the receiver. The orbital databases were checked, but no known object matched the timing and trajectory perfectly. Then there was the comet itself. Could the signal have been a real but transient natural emission from the icy body? Perhaps a sudden outburst of gas, a localized jet of material interacting with the solar wind in a unique way, produced a brief, coherent radio burst that lasted only as long as the eruption itself. By the time anyone listened again, the eruption was over and the comet had returned to its silent voyage. Without a repeat performance, the truth became impossible to ever know. The case was filed away, a single, unresolved entry in a log of cosmic maybes. Its legacy is not an answer, but a profound and frustrating question. In the search for signals, the ones that disappear are often more haunting than the ones we never hear at all, because for one fleeting moment, we thought we had finally caught the universe in the act of speaking. This precision in tracking, however, can sometimes reveal a deeper mystery. As astronomers plotted the arc of one particular interstellar visitor across the heavens, a small but undeniable anomaly emerged. The comet was not following the perfect gravitational curve dictated by the Sun and planets. Its path exhibited a tiny, persistent wobble, a series of minute deviations from its predicted orbit. These perturbations were too small to see with the naked eye, but in the precise world of celestial mechanics, they screamed for an explanation. The usual suspects were quickly ruled out. The gentle push from outgassing, that rocket effect seen in normal comets, was calculated and found insufficient to account for the drift. The gravitational tugs from every known planet, moon, and large asteroid were meticulously modeled and subtracted from the data. Yet the wobble remained, an unsolved equation written in the comet's own motion. So what unseen hand was nudging this icy wanderer off its course? One compelling theory points to a hidden companion. Perhaps this comet was not traveling alone. It could have been a binary system, a tiny, dark fragment orbiting the main nucleus, too small and close to be resolved by our telescopes. The gravitational dance between these two bodies would subtly shift the center of mass of the entire system, creating the observed wobble as they tumbled together through space. Another possibility lies in the comet's own activity, but of a most peculiar kind. Normal outgassing is somewhat symmetrical, like steam evenly escaping from a boiling kettle. But what if this comet's surface was a bizarre patchwork of ices and insulating crust? Jets of gas could erupt from only one region, acting like a lopsided thruster, imparting a tiny spin and a slight lateral push that gravity alone could not explain. Then there is the Yarkovsky effect, a subtle but powerful force that acts on small bodies in space. It has nothing to do with gravity or gas. Instead, it is a thermal effect. As an object spins, its sunlit side heats up. This warm surface later rotates into the cold shadow of space and re-radiates that heat as infrared light. This emission acts like a tiny photon thruster. For a large asteroid, the Yarkovsky effect can nudge its orbit over millions of years. But for a very small, fast-moving interstellar object, the mathematics become extreme and controversial. Could this thermal photon pressure, acting on a bizarrely shaped or spinning nucleus, produce the precise wobble we observed? Each explanation paints a picture of a far more complex object than a simple dirty snowball. It suggests a world of hidden structure, of uneven landscapes and secret companions, all revealed not by light or radio waves, but by the silent, impeccable grammar of its motion through the void. The wobble in its path hinted at hidden complexities, but sometimes the strangeness is written in plain sight for anyone with the right eyes to see. Radio telescopes capable of mapping the faintest whispers of energy in space turned their gaze toward another interstellar visitor and captured something utterly unexpected. Instead of the classic streaming tails of gas and dust that point away from the sun, the images revealed a faint, glowing halo encircling the comet's nucleus. It was a torus, a cosmic donut of radio emission, hanging in space around the icy wanderer. This was no ordinary cometary feature. Typical tails are sculpted by the relentless push of solar radiation and wind, like smoke blown from a candle. This ring, however, was symmetrical and closed, a perfect loop of energy with the comet at its center. The immediate question was one of origin. What physical process could create such a uniform, ring-shaped structure around a solitary object barreling through the void? The first, most dramatic possibility was a recent cataclysm. Imagine this comet had suffered a violent breakup just before or during its approach to the inner solar system. A cloud of debris shattered from the nucleus would initially expand in all directions. If the fragments were similar in size and composition, and if the breakup was recent enough that the solar wind hadn't yet swept the material into tails, this debris cloud could appear as a faint spherical halo. Over time, it would distort, but for a brief window, it might look like a ring. Yet, the ring appeared stable across multiple observations, arguing against a short-lived explosion. A second, more subtle explanation looked to magnetism. We know that some comets, when active, can generate their own weak magnetic fields as ionized gas from their coma interacts with the solar wind's magnetic field. Could this particular interstellar comet have a unique chemical makeup, one that produced ions in just the right way to create a self-contained magnetic bubble? Within this bubble, charged particles might get trapped, spiraling along magnetic field lines that themselves formed a closed, donut-shaped structure around the nucleus, emitting synchrotron radiation we could detect as a radio ring. This would be a rare and precious natural laboratory. Then, of course, there was the sobering third option, an artifact. Radio astronomy is a dance with inference. The data from telescopes is processed through complex algorithms to clean up noise and construct an image. Sometimes, the way we process the data, especially for a faint, moving target, can inadvertently create structures that aren't really there. A slight error in calibrating for the comet's motion, or an unlucky confluence of background radio sources, might be mathematically synthesized into the appearance of a ring by our own software. Each possibility tells a different story about the visitor. A debris ring speaks of a violent past and a fragile nature. A magnetic torus hints at a complex, active chemistry alien to our own solar system. An artifact is a lesson in humility, a reminder that our view of the cosmos is always filtered through the lens of our own technology. The interstellar donut, whether real or illusory, forces us to look closer and question not just the object but the very methods we use to see it. The radio torus was a ghostly structure, but the next signal was written in pure atomic light. As the light from another interstellar visitor was stretched into its spectral barcode, a single, faint line appeared where no one expected it. It was the unmistakable fingerprint of lithium, the third lightest element in the universe. This detection sent a quiet shockwave through the community of astronomers who read the language of starlight. In the comets of our own solar system, lithium is a ghost. It is virtually absent, an element that simply doesn't condense onto icy grains in the cold, quiet nurseries where our comets formed. Its presence in this interstellar wanderer was not just unusual, it was a profound anomaly. Lithium is a cosmic paradox. It is one of the three original elements forged in the Big Bang itself, alongside hydrogen and helium. Yet it is also incredibly fragile. The searing interiors of stars act as lithium furnaces, destroying it almost as quickly as it can be made. For lithium to survive and become part of a comet, it requires a very specific and violent history. The leading theory points to a stellar cataclysm. When a certain type of star, a classical nova, undergoes a thermonuclear explosion on its surface, it can blast vast amounts of freshly synthesized lithium into space. A supernova, the death of a massive star, can also seed its surroundings with this delicate element. The lithium in this comet's coma was a radioactive timestamp. It suggested this ball of ice and rock did not form in a calm, quiet disk like our own. Instead, it may have coalesced in the turbulent, chemically enriched debris field surrounding a dying star. Its very ices were infused with the ashes of a stellar explosion. Alternatively, the lithium could tell a story about location. Perhaps this comet formed extraordinarily close to its young, violent star, in a region so hot that more refractory elements like lithium could condense onto dust grains before being blown outward to the colder comet-forming zone. The abundance was the real puzzle. It wasn't just present, it was all wrong, either far too high or curiously low compared to every model. This left spectroscopists baffled, holding a chemical message they could read but not translate. The lithium anomaly is a whisper from a fundamentally alien birthplace. It tells us this visitor is not just from another star, but from a place where the very rules of cosmic chemistry were written by fire and catastrophe, gifting it with an atomic signature we find nowhere at home. The lithium signature spoke of ancient stellar fires, but some signals arrive as sudden, brilliant bursts of light witnessed by thousands. On a clear night, as an interstellar comet tracked across the sky, amateur astronomers across 3 continents trained their cameras on the faint visitor. Separated by oceans, they were united by a single, baffling sight. Over the span of several hours, each observer captured the same phenomenon, a series of brief, intense flashes of white light from the comet's nucleus. These were not random flickers. The flashes occurred in near-perfect synchrony, a cosmic light show pulsing on a schedule visible from multiple points on Earth. The global coordination of the observations ruled out local tricks of the atmosphere or camera glitches. This was a real event happening on the comet itself, a transient mystery unfolding in real time for a planet full of watchers. The immediate hunt for a natural cause began. One compelling theory focused on rotation. Imagine a dark, icy nucleus tumbling slowly through space, its surface a mottled landscape of ancient, sooty ice and patches of pristine, highly reflective water ice. As it spins, a bright patch could rotate into the sunlight, acting like a mirror suddenly aimed at Earth, creating a brilliant flash before turning away again. If the spin period was regular, the flashes would be too. Another idea looked inward to stresses deep within. As the comet warmed near the sun, internal pressures could build. Trapped pockets of volatile gas sealed under a thin crust might explosively rupture. Each tiny eruption would expose fresh, reflective ice and release a cloud of dust that brilliantly scattered sunlight for a few moments, a series of silent fireworks on a miniature scale. Yet the precise timing and similarity of the flashes gave some researchers pause, leading to more speculative notions. Could the surface have a highly geometric crystalline structure, perhaps a vast, flat facet that only aligned to reflect the sun directly toward Earth at specific points in its rotation? Or, in the most fringe of hypotheses, was this the glint of sunlight on some vast, manufactured surface? The synchronous flashes became a testament not to alien technology, but to human curiosity. This transient event, lasting less than a single Earth day, was documented in stunning detail because a global network of enthusiasts was looking. Their collective data created a record more complete than any single professional observatory could achieve, turning a momentary anomaly into a lasting puzzle. The flashes ceased as suddenly as they began, leaving behind only data and wonder, a reminder that some of the universe's most intriguing messages are written in a language of light, visible to anyone who cares to look up. Light itself can carry hidden messages in its orientation, a property known as polarization. When sunlight scatters off the tiny dust grains in a comet's coma, the light waves can become aligned in a specific direction, like the glare off a calm lake. By measuring this polarization, scientists can deduce the size, shape, and even composition of those distant dust particles without ever touching them. It's a powerful remote sensing tool that has classified the dust from countless comets in our own solar system into familiar families: silicate grains like tiny specks of sand, carbonaceous grains dark and sooty, or icy grains glittering with frozen volatiles. Then came the measurement of an interstellar visitor. The polarization data streamed in, and the usual models were applied. The numbers did not compute. The signature was an extreme outlier, a wild point on the graph that refused to cluster with any known type of cosmic dust. It wasn't silicate, it wasn't carbonaceous. It wasn't simply icy. The pattern of scattered light suggested dust grains with properties no one had catalogued before. A frantic theoretical scramble began. Could the grains be a bizarre hybrid material, a composite of ice and organics formed under unknown pressures? Perhaps they were not spheres or irregular chunks, but exotic, elongated needles or flat, plate-like structures that scattered light in a wholly unique way. Some researchers even pondered if the grains were incredibly porous, fractal aggregates so fluffy and tenuous that they behaved more like a cloud of microscopic snowflakes than solid dust. Each proposed solution pointed to a formation environment unlike anything in our local cosmic neighborhood. The polarization paradox is a quiet but profound revelation. It tells us that the very dust, the fundamental grit that clumps together to form planets and moons, can be assembled in alien workshops using recipes we have never seen. If the building blocks themselves are strange, what does that say about the worlds they might eventually create? Our solar system's dust is just one sample, one page in a galactic library of material science we are only beginning to read. Dust and gas should tell the same story, but sometimes they argue. In one particularly puzzling interstellar visitor, telescopes captured a scene that seemed to defy the basic logic of cometary behavior. As the comet swung around the sun, its beautiful curved dust tail composed of fine, reflective grains began to shine more brilliantly against the dark sky. This usually signals a surge in activity, more ice turning to vapor and blasting dust off the nucleus. Yet at the exact same time, the comet's ion tail, that straight blue stream of charged gas pushed directly by the solar wind, did the opposite. It faded, becoming wispy and faint as if the comet was running out of breath. This anti-correlation was a direct contradiction. In every comet we know, dust and gas are partners in a dance. More heat means more sublimation, which releases both dust and gas together. For one to brighten while the other dims is like seeing a fire grow hotter while its smoke disappears. To explain this ghostly decoupling, scientists had to rethink the comet's very architecture. One compelling theory imagines a layered world, an icy onion peeling back under the sun's glare. Perhaps this comet had spent eons in the deep freeze of interstellar space, accumulating a thick, dusty crust on its surface, a mantle rich in silicates and complex organics but relatively poor in volatile ices like water or carbon dioxide. When it first approached the sun, the heat sublimated the scant ices in that outer crust, releasing a burst of gas and the dust trapped within it, creating the initial tails. But as that dusty shell was completely blown away, it revealed a core with a shocking secret. The interior might have been gas-poor, a kind of primordial rubble pile where the most volatile compounds had already been lost or never existed in abundance. So the brilliant dust tail was the final, glittering cascade of that outer layer disintegrating, while the fading ion tail revealed there was simply little gas left inside to replace it. Another possibility points to chemistry rather than geology. Not all ices sublimate at the same temperature. Water ice turns to vapor at a certain point, carbon dioxide does so much earlier, and other compounds have their own thresholds. What if this comet was dominated by one specific type of volatile, a substance that vaporizes completely at a moderate temperature? Once that reservoir was exhausted, the production of gas would plummet, even as continued solar heating agitated and released any remaining loose dust from the surface. The comet would, in effect, switch modes from a gas-rich emitter to a dust-only object mid-flight. This would create the observed signal, a last dusty hurrah under a dying gas lamp. Both explanations paint a portrait of profound heterogeneity. They suggest these interstellar nomads are not uniform snowballs, but stratified time capsules with complex histories written in their layers. Their behavior is not a single, predictable reaction to sunlight, but a reveal of their internal story, page by page, as the sun turns each page to vapor. The comet was a fireworks display against the black velvet of space, a brilliant fountain of dust and gas that should have been shouting across every wavelength. Yet when radio telescopes listened for its voice, they heard nothing at all. This is the paradox of the hyperactive comet that fell silent. Visually, it was a textbook spectacle, boasting a vast, glowing coma and a sweeping tail that spoke of intense outgassing. All that erupting gas, primarily water vapor being blasted apart by sunlight, should have left a clear radio signature. Specific molecules, like hydroxyl radicals, emit at very predictable frequencies, creating a kind of cosmic barcode that radio astronomers can easily tune into. They pointed their dishes, calibrated their receivers to the correct channel, and expected a strong, clear signal. Instead, they were met with a profound and puzzling quiet. The silence was as loud as any signal. If the comet was so active, where was its radio song? The investigation turned to the nature of the coma itself. One leading theory suggests the coma was not made of the usual fine mist of gas and tiny dust grains, but of something much coarser. Imagine the difference between steam from a kettle and a cloud of blowing sand. If the outgassing was primarily ejecting unusually large, cold chunks of dust and ice, the total surface area for sunlight to interact with would be far smaller. The water molecules might be trapped inside these icy pebbles, sublimating slowly and never reaching the high densities in the coma needed to produce a detectable radio emission. The comet would look brilliantly reflective from scattered sunlight off all that coarse debris, but its chemical radio fingerprint would be faint to non-existent. Another possibility points to an exotic chemistry. Our radio searches are tuned for the molecules we know best, primarily water and its byproducts. What if this interstellar visitor was venting something else entirely? Its nucleus could be dominated by volatile ices like carbon monoxide or nitrogen, which have much weaker or different radio signatures than water. Or perhaps the outgassing was so violent and turbulent that the molecules were being broken down into simpler atoms before they could emit the specific frequencies we were listening for. It would be like tuning a radio to a classical station while the orchestra is only playing percussion. You might hear the beat, but you'd miss the melody you were searching for. Then there is the humbling possibility of simple cosmic misalignment. Our equipment is designed for the typical comets of our solar system. The precise frequencies, the bandwidth, the very assumptions about how the gas is excited are all based on a local sample. This hyperactive visitor, born around another star, might operate on a slightly different physical principle. Its emissions could be Doppler shifted just outside our search band, or spread over a broader range of frequencies than our receivers could capture at once. We may have been listening intently on one channel while its broadcast was happening on the next one over, a frustrating case of missing the message due to a subtle difference in dialect. This radio silence, therefore, is not an absence of information but a signal in itself, a clue that the most spectacular shows in the cosmos might follow a script we have not yet learned to read. Silence from one comet can sometimes reveal an echo from another, years after it has vanished from sight. This brings us to one of the most speculative yet captivating ideas in our catalog, the gravitational lens echo. The concept rests on one of Einstein's great predictions that massive objects warp the fabric of space-time, bending the path of light that passes nearby. A star, a galaxy, or even a black hole can act as a natural cosmic lens, magnifying and distorting the image of a more distant object behind it. But what about something as small as a comet? The proposal is audacious. Theorists have asked if an interstellar comet's nucleus were extraordinarily dense, a solid mountain of rock or metal rather than a fragile ball of ice. Its gravity, however minuscule, might be just enough to create a detectable lensing effect. As it passed directly between Earth and a distant, steady radio source like a quasar, the comet's gravity could briefly bend and focus those radio waves, causing a subtle but measurable spike in the signal we receive. The key word here is subtle. For an object only a kilometer across, the effect would be unimaginably faint, a whisper buried under decades of radio noise. The true intrigue, however, lies in the timing. Because this would be a gravitational effect, the signal would follow a specific pattern. As the comet approached alignment, the background source would brighten. At perfect alignment, it might split into multiple images, a hallmark of lensing. And as the comet moved away, the signal would fade in a symmetrical fashion. The most mind-bending part is the echo. Imagine an interstellar comet zipped through our solar system a decade ago. No one thought to check for lensing at the time. Years later, an astronomer meticulously analyzing old data from a radio telescope might notice a peculiar, unexplained blip in the records of a distant quasar. By tracing back the comet's known path and the quasar's position, they could find a perfect alignment on a specific date in the past. That blip would be the echo of the comet's passage, a ghostly signature recorded long before anyone knew to look for it. Proving such a claim is a monumental challenge. It requires the comet to be both incredibly dense and pass in front of a suitably bright and steady background source with exquisite precision. It demands radio telescope data of exceptional quality from that exact moment, data that is often not archived in the necessary way, and it must rule out every other possibility, from instrumental glitches to flares from the quasar itself. If such an echo were ever confirmed, its implications would be staggering. First, it would mean we had discovered a new class of interstellar object, not an icy comet but a rogue exoplanetesimal, a fragment of a shattered alien world dense as iron. Second, it would turn a simple comet into a tool of fundamental physics, a natural laboratory for testing gravity on a solar system scale. The gravitational lens echo remains a beautiful hypothesis, a testament to how far our thinking must stretch to interpret the silent passage of these wanderers. It suggests that some of their most profound signals are not emitted but cast like shadows from a distant, unseen light. Its surface should have been a deep freeze, but it glowed with a secret warmth. As the comet retreated into the outer solar system, the Spitzer Space Telescope turned its infrared eye toward the fading speck. This instrument doesn't see light, it sees heat, painting a picture of temperature. What it revealed was baffling. The comet's nucleus was radiating significantly more warmth than any standard model could account for at its vast distance from the sun. It was as if a block of ice left in the shadow of a deep freezer was somehow giving off the gentle heat of a room temperature stone. This anomalous heat signature forced scientists to consider that this traveler was not a simple, passive chunk of ice. Something inside was active, or its structure was hiding a profound secret. The first, most dramatic possibility was internal radioactivity. In our solar system, comets contain only trace amounts of radioactive elements. But what if this visitor formed in the debris cloud of a rare stellar event, like a neutron star merger? Such a cataclysm forges heavy, unstable isotopes. If the comet's rock and dust were laced with an unusual concentration of these radioactive atoms, their decay deep within the nucleus could provide a steady, internal furnace, keeping the core warm for eons. This would make the comet less a dirty snowball and more a slow, cold fusion reactor coasting between the stars. A second theory looks to a violent recent past. Tidal heating is a powerful force. When a small body passes extremely close to a massive object like a star, the gravitational pull can stretch and flex its interior, generating immense friction. Imagine taking a piece of clay and rapidly bending it back and forth. It warms in your hands, If this comet had a close encounter with its home star or even a rogue planet just before being ejected, that tidal energy could still be dissipating, leaving it warm to the touch long after the event. It would carry the fading body heat of a cosmic brush with death. Then there is the concept of primordial heat. Large planets like Earth are still cooling from their fiery formation. Could a comet, typically too small to retain such heat, be an exception? If it formed incredibly fast and early in a violently energetic protoplanetary disk, and if it had just the right dense, rocky core, it might have trapped a reservoir of formation heat under a perfectly insulating blanket of ice. It would be a tiny, fossilized ember from the dawn of an alien solar system. Finally, the most structurally bizarre idea, a thermos comet. Picture not a solid ball, but an incredibly porous, fractal aggregate of ice and dust, more like a cosmic snowdrift or a ball of froth. This fluff ball structure with countless tiny air pockets would be a superb insulator. The feeble heat from the sun during its brief passage through our inner system could have been trapped deep within this labyrinth, unable to escape back into space. The comet's own warmth, however faint, would be its prisoner, making it appear artificially hot long after it left the sun's vicinity. Each explanation points to an object of profound abnormality. Internal radioactivity speaks of a birth seeded by stellar catastrophe. Tidal heating tells a story of a recent gravitational slingshot. Primordial heat suggests a formation process far more energetic than our own. And an insulating structure defies our very image of a comet's solidity. This simple heat signature, a few points of data on a graph, whispers that some interstellar wanderers are not just cold visitors from the dark. They are worlds with hidden inner lives, carrying the fading warmth of their own extraordinary histories. The comet's hidden warmth hinted at a complex inner world, but the next revelation came from its very shape. High-resolution images from the Hubble Space Telescope revealed a visitor that was not one, but two. It was a contact binary, two distinct, icy lobes gently stuck together like a misshapen cosmic snowman tumbling through the void. This configuration, while rare, is not unheard of in our own solar system. The true mystery began when the two lobes, under the subtle stresses of solar heating and rotation, began a slow, silent drift apart. As a thin bridge of dust and gas formed between them, astronomers performed a remarkable feat. They pointed their spectrographs at each lobe individually, breaking their light into separate barcodes. The readings that came back were astonishing. The two halves of this single object told two completely different chemical stories. One lobe showed a strong signature of water ice and familiar silicate dust. The other, however, glowed with the spectral lines of carbon monoxide and complex organic molecules, a far more volatile and primitive mixture. It was as if someone had welded together a chunk of a rocky, watery world and a piece of a primordial, chemical-rich ice ball. This binary signal split presents a direct physical sample of two alien environments now traveling as one. The leading theory is a gentle, ancient merger in the outer reaches of its home star system. Picture two small bodies, planetesimals, forming in entirely different neighborhoods of the same protoplanetary disk. One may have coalesced closer to the star, where temperatures allowed water ice to dominate. The other formed farther out, in the deep freeze where carbon monoxide and other supervolatiles could condense onto dust grains. Over billions of years, their orbits slowly brought them together in a slow-motion collision, a gentle kiss that left them permanently entwined. Their union would have occurred before their star system ejected them into the galactic darkness, meaning they have been traveling together for eons. This makes the object a unique archaeological dig. It is not a random chunk of a single world, but a deliberate pairing of two distinct geological records from an alien solar system. The subtle separation we witnessed may have been the first time those two histories began to physically unravel since their merger, allowing us a fleeting chance to read each page separately. The binary comet is more than a curiosity. It is a fossilized snapshot of the diversity that can exist within a single planetary family, a direct message that even the smallest wanderers can carry the combined history of worlds that never were. Radar, the ultimate tool for seeing in the dark, was trained on the faint visitor. Scientists at the Arecibo and Goldstone facilities performed a remarkable feat, aiming powerful radio beams directly at the comet as it sped away. They were not listening this time, but shouting into the void and waiting for the faintest echo. The principle is simple: a radar pulse travels out, strikes the object, and a tiny fraction bounces back. By measuring the time delay and the nature of the scattered return, you can map surface roughness, shape, and even rotation. For a typical comet nucleus, the radar echo is a mess, a diffuse and muddled signal. The surface is assumed to be a chaotic, porous landscape of dust, rock, and ice, scattering the incoming energy in all directions like light hitting a crumpled piece of tin foil. The echo from this interstellar target, however, contained a startling anomaly. Buried within the expected noisy return was a spike, an echo that was too bright, too coherent, and too focused. It came from an area on the nucleus no larger than a football field, a pinprick on a cosmic scale reflecting radar energy with surprising efficiency. This was not the signature of a rough, natural surface. It was the signature of something unusually smooth or unnaturally geometric. The immediate scientific task was to find a natural explanation for such a sharp reflection. The first and most plausible idea involved composition. What if that small patch was not dirty ice at all, but a region of exposed metal-rich material? A slab of iron-nickel alloy, like the core of a shattered protoplanet, would act as a near-perfect mirror for radar waves, creating that intense, coherent bounce. It would be a window into the comet's violent past, a glimpse of its metallic heart. A second theory looked to geology rather than chemistry. Imagine a sheer cliff face of water ice, a smooth, vertical wall created by a past cleavage or landslide. If this facet happened to be oriented almost perfectly perpendicular to the incoming radar beam, it would act like a flat mirror, reflecting a concentrated burst of energy back to the source. The odds of such a perfect alignment are low, but in a universe of infinite possibilities, not impossible. Then there is the more speculative interpretation, one that borrows from human engineering. On Earth, we use corner reflectors, devices with three flat surfaces meeting at right angles to create ultra-bright radar echoes. They are placed on boats, satellites, and even the moon. Any radio wave hitting this configuration bounces directly back to its source, regardless of the angle of approach. The speculative question is, could a natural geological process create a perfect corner reflector in space? Could the fracturing of an icy body under tidal forces or thermal stress cleave a surface with unnaturally precise 90-degree geometry? While conceivable, such a formation would be a 1 in a billion cosmic coincidence. The radar return forces us to confront the limits of our imagination. We look at a speck of light and assume a world of gentle, rounded contours shaped by eons of gentle processes. But that coherent spike whispers of sharp edges, of sudden fractures, of exposed bones from a catastrophic history. It reminds us that these travelers are not just passive snowballs, but worlds with landscapes that can, in the right light, flash back at us with the blinding clarity of a signal. A comet's ion tail is a cosmic weather vane, a straight and true pointer streaming directly away from the sun. It is sculpted by the relentless solar wind, a stream of charged particles that blows with a force far stronger than any earthly hurricane. This relationship is so dependable that by watching a tail's motion, we can almost feel the invisible gusts and lulls of that stellar breeze. Yet one interstellar visitor presented a flagrant defiance of this celestial rule. Its ion tail did not flow smoothly. Instead, it jerked, kinked, and whipped about in chaotic spasms, as if caught in a violent, localized storm that existed nowhere else in the solar system at that time. Astronomers immediately turned their instruments to measure the solar wind itself, expecting to find a corresponding tempest of particles to explain the tale's dance. The data returned only calm. The solar wind was steady, a placid and unremarkable flow. The storm was on the comet alone. This disconnect pointed to a source of turbulence coming from the visitor itself. The leading hypothesis centers on a self-generated magnetic bubble. Most comets are passive, their gas simply ionized and swept away by the sun's magnetic field carried in the solar wind. But this object appeared to be active, fighting back. Its unique chemical soup venting from the nucleus may have created a dense, localized cloud of plasma. Within this cloud, electric currents could flow, generating a small but potent magnetic field around the comet, a protective cocoon of its own making. When the steady solar wind hit this self-made magnetic bubble, the interaction would have been chaotic and unpredictable. The two magnetic architectures would push and tangle, creating regions of turbulence and reconnection that violently whipped the ion tail, like a flag snapping in the eddies behind a speeding car. This suggests the comet was not just an icy rock passively sublimating, but a complex plasma physics laboratory, its interior chemistry so alien that it turned its immediate environment into a maverick pocket of magnetic chaos within the sun's well-ordered domain. The chaotic dance of its ion tail spoke of a complex internal chemistry, a truth that became undeniable when we finally read its spectral signature. The light from this comet's coma revealed a staggering anomaly, an organic molecule overload that defied every expectation. When astronomers broke its light into a rainbow barcode, they did not find the simple, sparse lines of water and carbon dioxide common to our solar system's comets. Instead, the spectrum was a dense, crowded forest of lines, the unmistakable fingerprints of a stunningly complex cocktail of organic molecules. Among them were precursors to life as we know it, including glycine, a fundamental amino acid, and even ethanol. This was not just a comet, it was a flying chemical warehouse, carrying a diversity of probiotic ingredients far richer than anything we have seen born in our own celestial neighborhood. The immediate question was one of origin. How did this wanderer become so chemically wealthy? One possibility is a spectacularly fertile birthplace. Perhaps this comet formed in an exceptionally dense and cold molecular cloud, a stellar nursery where complex chemistry had more time and more raw material to build elaborate molecules right on the surfaces of icy dust grains before they clumped together. It would be the difference between a sparse desert and a lush rainforest in terms of cosmic chemistry. An even more profound idea is that this comet is not a pristine sample of a cloud, but a processed relic of an entire alien planetary system. It could be a fragment from the outer reaches of a system where such organics were abundant, or even a piece of a shattered ocean world or a chemically rich protoplanet, carrying within it a frozen record of that system's advanced probiotic evolution. This leads to a fascinating and delicate puzzle, the puzzle of survival. Molecules like amino acids are fragile. The harsh radiation of interstellar space over millions of years should break them apart. So how did this comet's complex cargo endure its epic journey? The answer likely lies in deep, cold shielding. Imagine the comet's nucleus not as a uniform ball of ice, but as a layered cosmic onion. These delicate organic molecules were probably not sitting on the surface, but entombed deep within, protected by overlying layers of water ice and dust that acted as a radiation shield a kilometer thick. They remained in a state of suspended animation, a deep freeze that lasted eons, only to be released and revealed when our sun's warmth finally began to peel those protective layers away during its brief visit. This comet, therefore, delivers a double message. It tells us that the basic chemical ingredients for life can be assembled in abundance around other stars, and it demonstrates a cosmic shipping method, deep freeze encapsulation, that could successfully deliver those ingredients across the vast gulf between solar systems. It turns a passing visitor into a potential courier carrying not a message, but the very building blocks of one. The comet's rich organic cargo suggests a world of profound chemical complexity, but sometimes the most telling clues are not about what the comet is made of, but how it falls apart. As the comet vented gas, it should have released a chaotic cloud of dust in all shapes and sizes, from boulders to smoke-like particles. Yet data from specialized dust detectors told a completely different story. The particles streaming from this interstellar visitor were not a random assortment. They were almost exclusively within one incredibly narrow size range, a uniform spray of fine grains akin to perfectly sifted beach sand. In our own solar system, comets are messy. A typical outburst throws out a wild mix from microscopic specks to chunks the size of houses, creating a broad and predictable distribution. This comet's output was unnervingly precise, a single note where a symphony of chaos was expected. This dust grain size discrepancy is a puzzle of cosmic filtering. What natural process could so efficiently sort and eject particles of such uniform dimensions? One compelling theory looks to the comet's surface itself. Imagine it is not a jumble of rock and ice, but a vast, homogeneous layer of a single material, perhaps a sintered crust of pure water ice or a blanket of incredibly fine silicate dust. If this uniform layer erodes under the sun's heat through a very specific process like the steady, grain-by-grain sublimation of a solid ice matrix, it could release particles of nearly identical size as the bonds between them break in a consistent way. It would be like watching a sandstone cliff weather away, producing a predictable shower of sand grains, but no pebbles and no dust. A darker, more dynamic history could also explain the uniformity. This comet might be the surviving remnant of a catastrophic fragmentation event. Picture a larger parent body shattered by a collision or a tidal encounter with a star long ago. The violent breakup would have created a cloud of debris of all sizes. Over time, through a complex gravitational dance, only fragments within a certain narrow size range might have remained bound together or ended up on this specific trajectory, while the larger boulders and finer powder drifted away or were lost. What we are witnessing now would not be the natural erosion of a primordial object, but the steady disintegration of a pre-sorted pile of rubble, all the fragments sharing a common origin in that ancient explosion. This strange signature forces us to reconsider the very geology of these travelers. Is its surface a monotonous, engineered-looking plane worn down by a perfectly consistent process? Or is it a ghost, a pile of similar-sized shards from a world that no longer exists, telling us its history not through chemistry, but through the silent, statistical language of its own dissolution? A comet's greatest firework should happen at its closest brush with the sun, but the cosmos loves a contradiction. This visitor saved its most spectacular performance for the quiet, cold months of its departure. Long after its perihelion, as it was receding into the outer darkness, telescopes caught it suddenly flaring to life. Its brightness skyrocketed, and a brilliant new coma erupted around it, a violent outburst that defied the basic rhythm of solar heating. The trigger for this delayed explosion had to be something other than simple sunlight. One possibility is a slow-burning heat wave finally reaching a secret vault. Picture the comet's interior not as solid ice, but as a labyrinth of sealed chambers, insulated by meters of porous, dusty material. When the comet was near the sun, surface ice sublimated, but that heat took months to conduct inward through that fantastic insulator. By the time the thermal pulse finally reached a large, sealed pocket of volatile carbon monoxide or nitrogen ice, the comet was already far away. The sudden influx of heat would have vaporized that trapped ice explosively, blowing open a vent to the surface and creating the belated outburst. It was a slow-motion detonation, timed by the poor conductivity of its own strange geology. Another, more violent trigger could have been a pure accident. The space between stars is not entirely empty. It is sprinkled with microscopic dust and tiny pebbles, the gravel of the galaxy. Traveling at tremendous speeds, this comet could have slammed into a dense knot of this interstellar debris, a cloud too tenuous to see but substantial enough to act like cosmic sandblasting. The kinetic energy from countless microscopic impacts across its surface would have delivered a sudden, massive shock of heat, flash vaporizing surface ices and triggering the eruption. The outburst, then, would not be about the sun at all, but a testament to the rough roads of interstellar travel, a collision recorded in light. The most intriguing explanation, however, involves a transformation in the very architecture of its ice. Water ice can exist in two main forms in space. The familiar kind is crystalline, with water molecules locked in an orderly lattice. The other is amorphous ice, a chaotic, glass-like solid that forms when water vapor condenses in the extreme cold and vacuum of deep space. Amorphous ice is metastable, a frozen accident waiting to happen. When it warms, it doesn't just melt, it violently reorganizes itself into the crystalline form. This crystallization process releases a surprising amount of latent heat, and it can also release gases like carbon monoxide that were trapped inside the chaotic molecular matrix. For this comet, the warmth from its solar pass may have taken months to raise the internal temperature just enough to cross this critical threshold. Deep within its nucleus, vast deposits of amorphous ice suddenly crystallized, releasing a burst of heat and a torrent of trapped gas all at once. The outburst was a phase change, a silent, internal rearrangement that had been pending since the comet's birth in a frigid interstellar cloud, finally triggered by a journey near our star. This delayed explosion forces us to see comets not as simple timers set by sunlight, but as complex chemical batteries, storing energy in their atomic bonds and releasing it on their own mysterious schedules. A comet's brilliance is a promise of water. For every spectacular tale we see in our own solar system, the driving force is almost always the same, the sublimation of vast reserves of water ice. So when an interstellar visitor put on a dazzling display with a bright coma and a sweeping dust tail, astronomers knew exactly where to look. They tuned their most sensitive instruments to the specific frequencies where water vapor shouts its presence in the infrared and radio spectrum. They listened and they looked. The result was a profound and unsettling silence. Despite all the visual fireworks, the comet's spectral barcode was missing its most fundamental line. This was the missing water paradox, a beautiful, active comet that seemed to be running on empty. The immediate question was one of propulsion. If not water, what invisible engine was blasting dust off its surface and creating such a glorious show? The investigation turned to other, more exotic volatiles. On Earth, water is our primary volatile, but in the colder, outer realms of a protoplanetary disk, other substances can take that role. Carbon monoxide sublimates at a much lower temperature. A comet dominated by carbon monoxide ice would erupt violently even in the weak sunlight of the outer solar system, producing a brilliant dust tail without releasing a single detectable molecule of water vapor. Carbon dioxide is another candidate, a volatile common on Mars and in the Kuiper belt. A comet rich in dry ice could also drive spectacular activity while hiding its true nature from our water-seeking instruments. Then there is molecular nitrogen, the main component of Pluto's heart and of Triton's geysers. A comet with a nitrogen ice heart would be a profoundly alien object, venting a gas that is nearly impossible to detect with standard methods, all while putting on a masterful cosmic deception. Each alternative driver paints a picture of a birthplace far removed from our own experience. A water-poor comet suggests it formed in an exceptionally cold region of its home system, a place so distant from its star that even water froze solid and inert, while only the super-volatiles like carbon monoxide remained active. Or perhaps it formed in a disk with a bizarre chemistry, one where oxygen was scarce, locked up in rocks, leaving carbon and nitrogen to form the dominant ices. This single observation forces a humbling expansion of our models. We can no longer assume that comets, even brilliant ones, are water-bearing messengers. Some may be chemical imposters, their beauty fueled by the ghostly sublimation of ices we rarely consider, whispering of deep-freeze nurseries where the recipes for worlds are written in a completely different atomic language. The beauty of a single comet can be deceptive, for its true story might only be told in a crowd. This leads us to a statistical mystery that looks not at one visitor, but at the paths of many. When astronomers plotted the incoming trajectories of several interstellar comets, a faint and controversial pattern seemed to emerge. Their paths across the sky were not scattered randomly like stars. Instead, they appeared to whisper of a common origin, their radiant points suggesting they had all streamed in from the same general direction in the galaxy. It was as if we were standing in a gentle cosmic rain, and the drops were not falling from everywhere but from a single, distant cloud. The implications of such an alignment are staggering. If real, it suggests these are not solitary wanderers from unrelated stars. They could be siblings, fragments from a single, catastrophic event in a faraway solar system. Picture a vast belt of icy planetesimals like our own Kuiper belt, peacefully orbiting a distant star. Then, a gravitational catastrophe strikes. Perhaps a rogue star passed too close, or a massive planet was ejected, its gravity violently stirring the belt. The event would have sent a shower of fragments flying in all directions, a shotgun blast of icy debris into the galactic void. A narrow cone of that debris, by pure chance, might now be sweeping through our region of space. Every interstellar comet we detect from that shower would point back to the same tragic moment in an alien system's history. This idea, however, ignited immediate and fierce scientific debate. The central question is whether the pattern is a real signal from the cosmos or a phantom created by our own limited view. Our detection methods are profoundly biased. We find these objects when they pass close to the sun and brighten, but our survey telescopes do not watch the entire sky equally. They have blind spots, favored regions, and specific schedules. Could it be that the apparent alignment simply traces the areas of the sky we have watched most intently? It is like concluding all lost keys are found in the living room, when that is simply the only room you have bothered to search with a thorough light. Critics argue that with so few detections, only a handful of confirmed interstellar visitors finding any apparent pattern is more likely to be a statistical fluke, a random grouping that our minds instinctively try to turn into a meaningful constellation. The debate cuts to the very heart of how we do science. Proponents of the alignment point to advanced models that attempt to correct for observational biases, and they claim the faint signal persists. Skeptics demand more data, many more objects, before any such extraordinary claim can be taken seriously. This tension is not a failure, but the essential process of discovery. It forces better surveys, sharper statistics, and more humble interpretations. Whether the alignment anomaly stands or falls, it has already reshaped the hunt. It asks us to see these comets not just as individuals, but as potential members of a family, carrying within their ice a shared memory of a single, distant day of destruction. Then, as the last of the interstellar visitors dwindled to a faint speck on its way back to the eternal dark, it seemed to speak. A single radio telescope, one of the most sensitive ever built, was tracking its final hours. In the deep quiet, a signal bloomed. It was not a blip or a burst of static, but a complex, modulated radio transmission that lasted for several minutes. The signal possessed a haunting structure, rising and falling in intensity with a pattern that was neither random nor simply periodic. It was a whisper with grammar, a sentence written in pure energy as the comet crossed the boundary of our detection for the very last time. This was the final transmission, the strongest and most puzzling signal of them all. The moment the data was processed, a global scientific scramble began. The first and most urgent task was to rule out human interference. Teams cross-referenced the timing with every known satellite, aircraft, and ground-based transmitter within thousands of miles. They checked for solar flares, for bursts from distant pulsars, for any natural phenomenon that could mimic such a sustained and intricate emission. Nothing matched. The signal had arrived from the precise, fading point of the comet. The decoding effort split into 3 frantic paths. The first treated it as potential data. Cryptographers and SETI specialists ran the signal's modulation through every analytical filter, searching for mathematical patterns, prime number sequences, or embedded imagery. They found tantalizing hints of structure, repeating motifs within the amplitude shifts, but no key to unlock a message. It was a locked book written in an unknown alphabet. The second path pursued a natural explanation rooted in plasma physics. Could the comet's dying interaction with the solar wind have created a sustained, resonant oscillation in its fading coma? Theorists modeled scenarios where magnetic field lines, snapping and reconnecting in the tenuous gas, could act like a vast, natural radio antenna, ringing with a complex tone as the system fell apart. The signal's duration and modulation, however, pushed this idea to its breaking point, requiring a plasma instability of unprecedented stability and coherence. The third, most sobering possibility was that it was a phantom of our own, making a form of interference so rare and specific it had never been recorded before. Perhaps it was a bizarre reflection from a piece of space debris, or a fleeting malfunction in the telescope's own electronics that, by cosmic coincidence, aligned perfectly with the comet's position. Yet every diagnostic check came back green. The telescope was functioning perfectly. Today, that final transmission exists as a digital ghost, a few megabytes of raw data archived in a scientific database. It has not repeated. No other object has emitted anything like it. It sits there, a perfect unsolved cipher from a traveler that is now forever beyond our reach, a last whisper hanging in the void that asks more eloquently than any other signal what we were truly listening to. 25 signals, each a unique fingerprint of mystery in the void. From tumbling shapes that accelerate without cause, to chemical signatures that defy all expectation, and fleeting whispers on the radio that vanish before they can be understood. This is the legacy of our first conversations with interstellar space. Each comet is more than a visitor, it is a messenger. It carries within its frozen heart the unedited history of an alien solar system, a record of temperatures and collisions, of chemistry and catastrophe from a place we will never see. They tell us that the recipes for building worlds are infinite in their variety, and that the delicate ingredients for life itself are not rare treasures but common cargo, shipped across the galaxy in deep frozen vaults of ice and rock. These unresolved mysteries are not failures of science but its very engine. Every unexplained acceleration pushes us to build better telescopes. Every bizarre spectral line demands more sensitive detectors. Every enigmatic signal forces us to question our assumptions about the nature of reality itself. Our curiosity is a form of cosmic echo, bouncing back against these silent travelers and returning to us as new technology, new understanding, and a deeper humility before the universe. So the next time you find yourself under a clear night sky, look up. That darkness is not empty, it is an ocean, and we have just begun to dip our toes into its waters. By supporting scientific research and nurturing our own sense of wonder, we keep our receivers tuned to the cosmos, because the next faint dot, the next whisper from the dark, could be the one that carries a signal so clear, so deliberate, that we finally understand we are not just listening to the universe, but that it is, in its own silent way, listening